Bismillahirrahmanirrahim. Assalamu alaikum, ladies and gentlemen. I know you are now well aware of me, and we are going towards our final destination. This is our start, and we are in the process of 6th lecture. Now we are taking a big turn here, as our subject is quantitative technique. So from today we will be using the first quantitative techniques that is mostly used, and you can say now it is currently it is not used, but it was widely used a few years ago, but it still holds, and we will start from our discussion of the first quantitative techniques, that is the correlation. Before going through this situation and this technique, I would like to give you a glimpse of the previous 5 lectures very briefly. In the first lecture, if you remember, we talked about how the quantitative techniques works and what is the importance of quantitative techniques, and we came to know that the quantitative techniques are extraordinarily important for all kinds of discipline. It is not confined to only 1 or 2 disciplines. Then we started studying that how this quantitative technique approach works, and we saw that it works systematically, starting from the identification of the problem to the implication of the issue, and we went through different stages and we talked it in detail. After this, our issue was to talk about the data. Data is very important, and we talked about what are the kinds of data, primary, secondary data, and how to collect data over this. Then we also had a detailed discussion over the sample, population, statistical technique, sample, and probability sampling procedure, and the non-probability sampling procedure. In the meanwhile, in this area time, we also studied some of the basic concepts of mathematics, like as the derivatives, as well as some basic concepts of probability. For example, the subjective, objective, and the other kinds of probability, how to add them up. Today, now what we are going to cover for today, we will be talking about the correlation, the causation, and the regression. So let me start with the first slide, and this is about the correlation. It is necessary to have look at what the correlation is. It measures the degree of relationship, that how much the variable are related to each other between the variables. Most of the time we will confine ourselves, restrict ourselves to 2 variable case, and we are presuming that we are taking the correlation between 2 variables. So it measures the degree. I am emphasizing the word degree. It will tell us that how much the variable are associated with each other, whether they are associated strongly, or there is a very, very weak or even no correlation between the variables. So the degree of association, we will denote it with a specific symbol, that is R. You can see that this is the R. If I go to the slide, we will be showing it by the R. We will be showing that this is the R. So this will be, and this R will be called the coefficient of correlation. It will tell us, we will now concentrate on its degree, and we will see that in which side its degree is going. The first characteristic, or you can say the first characteristic of this correlation, it can be positive as well as negative. No restriction on the value. Now I am talking about the association. It is association, and now I am talking about the degree of association that we have denoted with the R. So what we will see, that what is the numerical value of the R. So first of all, we discussed its first property, that it can be positive as well as negative. So like probability, that could be only positive. There is no restriction on this correlation of coefficient, that whether it is positive or negative. but it has a certain range as the probability ranges between 0 to 1. Similarly, the coefficient of correlation ranges between -1 to +1. So its range can be written that the coefficient, it is greater than or equal to r and less than the coefficient of correlation is greater than equal to -1 or less than equal to 1. So we have specified its two range. First range is this is that I can say that this is the +1 and the other range is -1. So the correlation cannot across these boundaries, it is between these two limits. It has two extremes, one +1 and other is the -1. What is the, first we will see that what is the positive correlation and what is the negative correlation. Positive correlation states that both the variables are going in the same direction. For example, if I say that this is assume this is the x variable and this is the y variable, and I say if x is increasing, the y is also increasing. This is a positive correlation. And at the same time, if x is decreasing, at the same time y is also decreasing. So this shows the variables are going into the same direction. If one is increasing, the other is following it and it is also increasing. And if one is decreasing, the other also follows it and decreases. If we have a practical example, we will see that there is a relationship between the supply and price. Here is the supply, here is the price, and there is a positive correlation between the supply and the price. What this says that as the price increases, the suppliers are more willing to sell their commodities in the market. So the range of the correlation coefficient is, we will be talking about its formula also, but still we are looking at some of the basic characteristic of the correlation coefficient. So it ranges between -1 and +1. So what is this? For example, if I say that this is variable x and this is y, and if there is such kind of the situation, and immediately you should be able to guess that the now relationship is negative. Now how much relationship is it 100% relationship? 100% mean because now it is minus. Is it -1? No, it is less than -1 because all the dots are not on the same line. I will be also showing that what is -1 and what is +1. So I can guess that it is equal to -0.60. 60% there is correlation between this. And what is the minus correlation when it is 100%? So this is the situation, this is x and y. First keep in mind that we are talking about the negative correlation. So what this is 100% negative correlation between the x and y, and here the correlation coefficient is -1. Similarly, I can go on the other extreme and I can say that this line is the relationship between two variables x and y. Now I am sure you will be guessing about that the correlation coefficient between x and y at this stage is 1. And if there is no correlation, zero correlation, what this means, if I draw the diagram of such kind, this is x and this is y, if I take that there is such kind of relationship between x and y values, you should be able to guess that the correlation between these two values r is equal to 0. We can't say that when one value is increasing, what is its effect or impact on the other dependent variable. So if such kind of situation, you may be asked, you may go through some of the diagrams and you should be in a position to look at the graph, and you should be able to in a position to predict what is the coefficient correlation. So come back here. Now you can say the more correlation coefficient, this is now 0, The more coefficient correlation is away from the zero, the more strong association between the variable. Now, just for ignoring plus and minus, just keep in mind that as your correlation coefficient is away and away from the zero, it is showing that there is a strong relationship. Now, if it is on the left side, or you can say on the minus side, then it shows that there is a strong relationship between the correlation, and the relationship is negative. What is the negative relationship? Negative relationship is that one variable is increasing, x is increasing, and on the other hand, y is decreasing. I was talking about the negative relationship. I showed that as the x increases, y reacts in the other direction, and it decreases. And if x decreases at the same time here, x decreases, the y starts increasing. So this is the relationship. From practical example, we can say that this is demand and this is supply, this is price, and there is a negative relationship between the demand and price, because as the price increases, people reduce their demand for purchasing of those commodities. So here, what the first characteristic of the coefficient correlation is, it never can cross -1 and 1 limit, +1 limit. It remains between -1 and 1, and it can even touch both the limits. -1 means there is a strong negative correlation between the two variables, and if there is a positive 1, it means that there is a strong positive correlation between the variables. The more it is near to 0, it means the correlation is becoming weaker and weaker, from whether it is negative correlation or whether it is a positive correlation. So the degree of association is measured by the coefficient of correlation. Now I would like to give the formula for this. What is the formula of this? This is the simplest formula you should remember for this. This is R, the correlation. And what is this? N summation xy minus summation x summation y divided by this. This term is in the numerator, and in the denominator it is n summation x square minus summation x whole square multiplied by n summation y square minus summation y whole square, and this is the bracket. So how we calculate this R? This is the coefficient of correlation that shows the degree of association. So first characteristic is that its range is between -1 and +1. What is the third characteristic? The first one was it can be positive or the negative. The second, we set a range for this. The third is it is symmetrical in nature. This is very, very interesting. What this means, the correlation of x with y is equal to the correlation of y with x. So it means the arranging of the variable doesn't matter. It is symmetrical in nature. So I was talking about the correlation coefficient. The second characteristic is this is symmetrical in nature. Symmetrical in nature mean is that the correlation between x and y is equal to correlation between y and x. For example, this is the correlation coefficient. Rxy is equal to Ryx. Here, if it is a series x, for example, it is 1, 2, 3, 4, and there is y series that says 0, 9, 6, 2. And if we measure the correlation between x and y, it will be, for example, I say that the correlation between these two terms is 0.60. So Rxy will be equal to 0.60, as well as Ryx is also equal to 0.60. So it is symmetrical in nature. Symmetrical means the arranging of the variable has no importance. If even we take x first or y first, there is no effect on the value of the correlation. In regression and causation we will be talking about something different, but here we are saying that the correlation coefficient is symmetrical in nature. The fourth characteristic of this is it is independent of origin and scale. This is another very interesting characteristic of the correlation coefficient. What this says, that it is independent of origin and the scale. For example, if our variable y, one variable is y, the other is x. If I say that I generate a new variable y star, and how I generate, I say that y star is equal to y plus 5. I add 5 to each of the term here, and if I want to draw it here, I can write it that this is a series y star. Now add 5 numerical value to each. This will become 11, this will become 14, this is again 11, and this is 7. So now there we have created a new variable, that is the y star. And again I say that I also want to generate another variable x star, and I say that x star should be equal to x plus 3. So I add 3 values to x, and I make a column here, and I say this is x star. So what is add 3? This will become 4, this will become 5, 8 and 7. Now rather than taking the correlation between x and y, we take the correlation between the new generated series, that are the x star and y star. So how I will write it, this, that r star, r x star y star is equal to r xy. What this means, we have changed the origin by adding some very numerical value to the x and y, but when we calculated the correlation coefficient was same, and in our supposition it should be equal to 0.60. Here I would like to mention that we are going to also do some practical work on the statistical software that is called the eViews, that will help you to run your regression in the statistical package, because when you will be collecting data, then you will be making some of trying to get some statistical inference. You will have to analyze data. It means you have to apply some of the techniques, and we will be using eViews. For right now, it is good time that I came to know that it is a very user-friendly software, and it is good time to tell you that you should immediately install eViews on your laptop. Definitely you will be wondering about that, how to install eViews. You can download eViews from the Google, and it will be the trial version, and it will work for you, because we will it can be further again and again installed over. So first my message is, we may be starting it after 1 or 2 more lectures. We will be proving all this by making some of the mathematical calculation. Although here is formula, if I go for that formula to calculate manually, it will consume a lot of time, and we have limited time we will have to go through. So it is my suggestion, and I will be telling you only 1 lecture before, that from the very next lecture you will have to install eViews on your laptop, and I am sure you are listening me on your laptop, and each and every student has the laptop facility. So what I was talking about, coming back to my discussion, the correlation coefficient, the correlation is independent of scale and region. What this means, if we multiply or divide the correlation, the series x or y by any of the positive value, we will say that there is no change in the correlation coefficient. We will be proving it at later stage. So these were the 4 characteristics of the correlation coefficients. Very simple. This is the techniques. As I said, that this is the techniques, the first quantitative techniques. In the previous years, before the, you can say, the wide application of the regression, there was a large use of, you can say, the extensive use of correlation between the variable. It tells us that whether the variables are correlated or not, but we will see that nowadays it is not sufficient to say that the one variable is depending on the other variable. After completing my discussion on the correlation, I will go towards the causation versus correlation. Before running towards the regression analysis, I want to make clear some of the basic concepts that you do not confuse yourself within these concepts. So I am sure now you are clear about the correlation. It is only a measure of the degree of the association between the variables, say x and y, a and b, and we have studied this characteristic. So what is the causation? Causation is something different. Causation means that there is cause and effect. For this, what this means, that one variable is causing the other and it has effect on the other variable to whom it is causing. For example, if I say that I would like to write here on this, if I say that if x causes y, so x is causing y, so it is not equal to that y is causing x. But in correlation coefficient, you know this, that the arranging of the variable doesn't matter. So first difference between the causation and the correlation is, in causation we are concerned with the cause and effect of the variable, but in correlation we are measuring just the degree of association. We can't say in correlation that whether x is causing y or y is causing x. The second difference between causation and correlation is that the causation is asymmetric. Asymmetric means that if I say that y is a function of x, it is not similar that x is a function of y. So it means the arranging of the variables is very, very important in cause and effect relationship. On the other hand, we have just proved that in correlation, that measures only the association, the arranging of the variable doesn't matter. It is symmetrical in nature, that a correlation between x and y is equal to the correlation between y and x. And the third difference is, causation is necessarily correlation. Now you will have come to know that if one variable is causing the other variable, it is definitely, then there is correlation between x and y. On the other hand, if there is correlation, it is not necessarily the causation. The correlation may exist there, but there is no theory, and you can say no guarantee that the variable one is causing the other. They are only correlated, but the causation doesn't exist. I would like to repeat this concept again, that what is the causation is necessarily correlation. If you find the causation, assume that this is the correlation exists between the variable. But if you find that there is correlation between the variable, you can't assume on any ground that there is causation between the variable. So here was a bifurcation between what is the causation and correlation. Simply speaking, correlation only a very weak measure of measuring the association. It measures how much the variables are correlated. But the causation is something different. It is asymmetrical as compared to the correlation, that is the symmetrical. And the important point to be noted here is that when there is causation, there is correlation also. But when there is correlation, it is not necessarily that there may be causation. I would like to give one example that I will repeat on later stage. For example, if here this is the x, I say this is x is the number of person in Pakistan. This is 10 value, 20, 60. Rather than number of people, I say these are the commodities. You can say 10 bread, 20 bread, and 60. And if y is the number of donkeys in United States, I say this is 100, this is 160, and I assume that it is 80. Now if you measure the correlation between these X and Y, X is the number of breads in Pakistan and Y is the number of donkeys in United States, you will come to know that the correlation exists there. You will, if you find through the correlation coefficient, there will be correlation between these two series, but you can't say that if there is correlation, there is causation, because the number of donkeys has nothing to do number of breads in Pakistan. So this is the difference between causation and the correlation. We will be using some of the notation. Now we are going towards the widely used concept regression. Before reaching that concept regression, we will use some of the notations. If you look at that side, these notations can be used alternatively. You do not kindly do not confuse yourself that, for example, for the dependent variable, I will write here that here dependent variable is y is a function of x. So here y is our dependent variable and x is independent. So dependent variables have many names. For example, we will call the dependent variable as well as the explained variable. So if you help me from y and x, we can easily spot that y is our explained variable. Similarly, if we go on the other side, the variable that is on the right hand side of the equation, those are called the independent variable. So against the dependent variable, there is a name for the other variable, that is the independent variable. So the column shows that we can give many names to the independent variable. At the same time, there are many names for the dependent variable. It is interesting that I will be using any of the name for the dependent variable and I can use any of the name for the independent variable. So therefore it is necessary to give you some glimpse of this, that which name we can call for this. Coming to the second one, this is explained variable, and when we will be giving the explained variable, oppositely we call that these are the explanatory variable. It could be one variable if there is only one x variable, and it could be more than one, that could be, we will say, more explanatory variable. This is the predictant. Dependent variable is also called the predictant, and at the other side this will be called the predictor. So predictor is the explanatory variable, predictor is the independent variable. On the other side, predictant is the dependent variable, predictor is the explained variable, as well as we can call it also the dependent variable. Just one step further, this is the regressant, and against this name we call the regressor, that is the independent variable. The other name for the dependent variable, that this is the response. It will give response when we will be stimulating our independent variable, and against this there is a stimulus variable. Stimulus variable immediately go up, it is the independent variable, and the response is the dependent variable. Definitely dependent variable give response when we stimulate the independent variable that we will change. Then there is another name for the dependent variable, that is the endogenous variable, and against this name there is another name for the variable, that is the exogenous variable. This is the outcome variable, that is called also the dependent variable, and this is the covariate variable. This is named for the independent variable. This is the controlled variable. We have controlled, and this is the control variable. And at the end, last but not the least, there are also other names. You will be a bit surprised that why there are how many names. Different books use different notation for the dependent as well as the independent variable. Sometime on the left hand side equation we say that this is the dependent variable, and all the right hand variable are said that these are the right hand side variable, and these are the independent variable. I will be using, although I am free to use any of the notation for the dependent as well as for the independent variable, but most of the time I will be using the word dependent variable for the dependent variable and independent, this one for the independent. And sometimes I will be also using this regressant, and this is the regressor. So, and sometime also endogenous and the exogenous. So out of these many options, I will restrict myself only to 3 that I will I will say the dependent variable, independent variable, the regressant, the regressor, and the endogenous as well as the exogenous variable. Now what is the regression? Very, very interesting concept. Regression has a history. There was a German statistician, that was the Francis Galton. He introduced the term of regression. He made an experiment, and it was a very, very interesting experiment, and on later stages it became the law of regression of, or you can say the Galton law of universal regression. So we will be going into the back history of this, that what Galton found and what was his inference from this experiment. So come here. The Galton noticed that if there are 2 groups of people, for example, these are the fathers and these are all the tall fathers, and oppositely there are short fathers. No need to worry about that here the number of father is greater and here is lower. No need to worry about. Just assume that the population is divided into 2 groups, very small population. One is the people who have extraordinary heights, and the other is who have extraordinary small heights. So what he found that the people who are taller, their children are also taller. Their children are also taller. And interestingly, the similar situation was this: the people, or you can say the fathers or the families who were tall, who were short, or you can say their height was small, their children were also small. Their height was also low. But interestingly, if you see that the height of the tall family's children was lower on average as compared to their father. For example, if I say that the average of all their father was, for example, 8 feet. They were very tall also, but I can say that the average height of these people was 7. So what this says, that although the father was very tall, the children were also tall, but what happened? The average decreased. Now come to the right hand side. Here the families are who have very small heights. Their children has also very small heights. For example, these people have 5 feet heights. Their children has also small heights. There the height may be 5.25 feet. So this Galton found, and what he found, that if there are 2 abnormal situations, abnormality exists in the population, ultimately it regresses toward average. So if you see, for example, if the average of the population is 6 feet, so these families over time, over generations and generations and generations, this will ultimately come towards 6 feet, and here who have small, they will ultimately come towards this 6 feet. So this was very interesting finding, and this became the universal law of Galton. What is the universal law of Galton? It states that the average height of children tend to move or regress the average height of the population as a whole. You can see from here that from smaller population height and from taller, it is regressing in this way. The taller is coming down and the shorter is coming up, and ultimately they are moving towards, they are converging towards, they are trending towards, and they are regressing towards the population. And what is the implication for us? That if there is unusuality or extremality exists in the population, in the long run it will ultimately converge towards the population mean, you can say that the population average. So this is called the fundamental or the universal law of Galton. So I would like to just give the definition and then I will go for the further step. That what is the Galton law of universal? The average height of children tend to move, in this our example, the average height of children tend to move or regress the average height of the population. We assumed each and everything here. Do not confuse yourself that this is the true situation. This is the hypothetical situation in which we say that this is, if we started from a very tall height, 8 feet, this may be not happening in the reality, and we started very from small, but I think on the shorter side it is the common, it is not something as unusual. There was a friend of Francis Galton, and his name was Carl Pearson. He also collected data on the 1,000 families, and he also noticed that the unusuality or the extremality converged towards the average of the population. In any case, you can prove this by taking the weights. Take maximum weights, take lower weights, and ultimately you will see over the years, if there is the normality exists, this high weight is not due to any of the disease, then you will see that over the long run that it will convert towards the average height. So this was very interesting result. So now I would go towards the modern concept. This was the very simple concept that gave the Francis Galton, and I am not sure about, but I think it is in the late 1880s. So it means more than 150 years this is the situation. But now the regression is used in some different context. What is its modern and different concept? Now regression analysis is not confined towards that, whether it converges towards the population mean or not. It is converged. It studies in regression. Now we studies the dependency of one variable, that is called the dependent variable. From right now I will call it the endogenous variable, and I will call the explained variable also. That now in modern concept we are interested in the dependency of the variable, that is the dependent variable, on one variable or more than one variable. And what is our view? With a view to estimate or predict. This is very important, that what we want, our object is to estimate the average value, estimate or the predict the average or the mean value of the dependent variable. dv here mentions dependent variable in terms of the given fixed values of the known. ev means explanatory variable. So what is this? Again I would like to, this is a bit large and the information is congested there. I would like to give the modern concept of regression here. In modern concept, we want to measure the dependency of the dependent variable with respect to the explanatory variable, and we are interested in predicting or estimating the average value or the mean value of the dependent variable on the basis of fixed, I would like to say again, on the basis of the fixed values of the independent variable. I will just explain that what this means. So here are two examples. The first is son's height and father height, and we will be taking other example, height at different level. So I was talking about that we want to, we are interested in the modern concept that we are going to measure the expected value of y, that is the mean or the average value, on the basis of the fixed values of the independent variable. So if I want to give that, look at this diagram. This is now the height of father, height of fathers, and this is height of sons, height of sons. So what this means, the height of the sons depends on the height of fathers. So if I say if there are fathers who have height of 60 feet and I say that their children have height of this. So this I say that they have height of, here is 60, some are above 60 and some are, here I say now we have fixed the value of the x at 60. If there are fathers whose height is 70, there are their sons, many sons, I can take 10 families, then there is also 80 and they have their sons of this. The values are also increasing here also. This is 60, this is 70 and this is 80. Now if I draw a regression between this, it will go through the means. For example, the mean of this is here, the mean of this line is here and this is here. So what this means, this is the regression line. So this is important. It says, what this says, it tells a very interesting story that as the height of the parents or the father is increasing, the height of the sons is also increasing, but the height of sons is not as increasing at the same rate as the height of fathers. Both heights are increasing, but the height of the sons is not increasing at the similar rate of the fathers. How we come to know? If we take the slope of this curve, that is the regression line, that is delta, if the son's height, change in son's height divided by change in father's height, so we will come to know it should be less than 1. If it is equal to 1, it means both the heights are increasing at the same rate. If it is less than 1, it shows that the independent variable is changing at a higher rate, while the dependent variable, that is here, that is the height of the children, is increasing at a comparatively low rate. So this is, I can give another example of you people. For example, I take here age and here your weight. I take that when your age was, not only 1 means you 1 people. If I take that when the age of the student is 10, assume that most of the time their weight is such kind of. Some are below 35, some are above. I can take many children at the age of 10. Then the children, when they reach the age of 15, their weight increases. So I can say that it can go up to 40 kg. These are also scales, as we did in the case of there. This is also scale. So when they reach the age of 20, there were also increase in their weight. So if I think this is the regression line that is going through the mean value. This is the mean value. What is mean value? That when the age of students was 10 years, then their average weight was round about 37 kg. And similarly, age is increasing, the mean weight of the student is also increasing, and similarly it goes on. So what was my purpose? To give this kind of 2 example. The purpose of to give you that in the modern concept of regression, we are interested in measuring the average value. You can see here is the average value, here is the average value, here is the average value, here. We are interested in predicting the average value of the dependent variable on the basis of the fixed values of the independent variable. Here the father's height is fixed at 60, 70 and 80. Here the age of the student is fixed as 10, 15 and 20 years. If we saw here that both our regression confirm the law of universal law of regression that was presented by the Galton. How they say, if we take the slope of these both curves, we come to know that these are less than 1, and what they shows that as the independent variable is increasing, dependent variable is also increasing, but the rate is lower in case of the dependent variable as compared to the independent variable. Now, statistical versus deterministic relationship. Immediately when I looked at the style, I came to know that if I can trust my memory, I explained this topic when we were talking about how the quantitative techniques work, because when we jumped from the mathematical model to the statistical model, we were discussing the similar things. So I will be just talking about this and refreshing your memory, because now we are entering into the new domain, that is the domain of the regression. That is the very, very interesting domain. So what is this? Regression concerns with the statistical relationship, not deterministic relationship. Regression, you should remember this, that in regression we are concerned with the statistical. Statistical relationship is that now there is margin of error, or you can say that there is risk of some kind, and there is not accuracy as 100%. This is not the functional or the deterministic dependence variable as in physics. Let me explain it. I am talking about that in regression, the relationship dependency is in the system is of the statistical nature. It is not of the deterministic nature. How we can give the example, the same example from there? Look at here. We are taking two trends. Here, this is functional or deterministic, and on the other hand, this is statistical. All the regressions in social sciences are concerned with the statistical relationship. So I will give the example for both things, and then we will come to know, and I am sure you have some of the memory, what it is the deterministic trend and what is the statistical trend. For example, if you come on this side, you say that the crop yield, this is our dependent variable. Crop yield depends, its function of many variables. For example, this is the fertilizer, F, the weather, the rain, the sunshine, SS mean sunshine. So if we look at this variable can be measured accurately, because we know how many packets we have thrown into the field, for example 1 acre or 1 hectare. About weather, we know there may be hot or there will be winter, but we can't accurately we can measure this. Similarly, there is rain. We can say that this year there will be more rain, there will be less rain, but to measure this accurately, we are predicting for the future, because we have the data about, if we go to the previous, we have the data on the millimeters rain in different areas. But we are interested in the predicting the average value of the dependent variable on the basis of the independent variable. Here you are independent variables. So the relationship between the crop yield and now the independent variable is of the statistical nature. It cannot be measured 100% with the accuracy. Now come to here, I would like to give one example, and then I will again compare. We are taking the example of the functional or deterministic trend, and we are comparing what is the deterministic trend and what is the statistical, because in regression we are interested in the dependency of the variable, and dependency doesn't mean that we are just concentrating on the deterministic trend. In our regression and in social sciences, we are determined for the statistical nature. It is not our choice, it is the ground reality that there is not a deterministic relationship between the dependent and the independent variable. Coming here, there is a fundamental law of Newton that F is equal to K into M1 M2 R square. This is the fundamental law of gravity of the Newton. What this law says, that any two particles in this universe attract each other with a force, and that force is proportional with their masses. Look at here, this force is proportional with m1 and m2, and it is inversely related with the distance between these two, m1 and m2. So this what laws, and the k is a constant, and we know the value of the k. We can measure m1, mass of first particle, m2 the part of mass of second particle, and this is the r square, the distance between the two particles. So this is a very deterministic trend. If we have the values, we will find the value, for example 1.76. This is the deterministic trend. It is not the, you can say, the topic of social sciences of the regression. But it is very interesting that if it at any time any of the independent variable becomes random, not fixed. For example, I say that when we try to measure the distance between two, there was some mistake. So immediately our model becomes statistical. So we say that now this model is not deterministic trend, it is of the statistical trend. After explaining this, my concern was to say that in regression we are concerned with the statistical nature of relationship between the variable, and which are the variable. One is the dependent variable, and there may be one or more than one independent or explanatory variables. Now I would like to give some comparison, as I did in the case of causation and the correlation. I would like to give some of compare both the terms that I have just explained previously. What is the statistical relationship and what is the functional, and what are the commonalities and the differences between the two? First is that the statistical relationship also concerned with the dependency of the variable, and similarly the functional or deterministic trend also concerned with the dependency of the variable. So it doesn't mean this thing is common between these two, statistical and deterministic trend. The second is variables are random. In statistical side, the variables are random, that they are that we cannot measure them. But on the other side, if we go towards the functional or deterministic trend, variables are not random. Go to your previous example. K is not random. We know the exact value of k. M1 we can measure, M2 we can measure, and we have also the concrete value of the r, and we can square it. But on the other side, we have no value of the variable wk, and sunshine are random. They cannot be measured accurately. The third is that here at the left side there is the statistical dependency. I have explained it in detail, and on the right hand side there is deterministic or functional dependency. The second last is it cannot be predicted with accuracy. The statistical model cannot be estimated with 100% accuracy. At least there is some portion that is unexplained due to the randomness of the variable. On the right hand side, it can be predicted with 100% accurately. I remember I gave you the example that if the scientist and the astronomist knows that what is the distance between the Mars and the Earth, what is the speed of the Curiosity robot that is nowadays on the Mars, and if they know each and every variable that is affecting the speed or the functionality of the curiosity, they can tell with even the accuracy of the microsecond that in how much time this curiosity robot will land on the Mars, although there is a million kilometers distance between this. That is the deterministic trend. So there should be there is 100% accuracy. And again, I would like to say that if it misses, curiosity robot lands 1 microsecond before or later than the expectation of the scientists, the model becomes random and or the statistical. Now there is other confusing between the students, that they think that regression and it is the causation. So we will differentiate that what is the regression and what is the causation. Although the regression analysis deal with dependency of one variable on the other, it does not necessarily imply causation. Although we can say that one variable depends on the other, but we can't say that this is also there is a causality. I will give the example. A statistical relationship, however strong, can never establish causation relationship. Statistical relation जितना भी strong सामने हमारे आ जाए, हम ये नहीं कह सकते कि that there is a relationship between the there is causality between the variable. There is no statistical reason. Now come to the previous example here. Who told us that the weather affects the crop? If I write in this way that the weather is a function of crop yield, this is also regression. Now who has told me कि आप वेरिएबल वेदर को राइट साइड पे ही रखें, क्योंकि जब वेदर चेंज होता है तो क्रॉप yield जो है वो इफेक्ट होती है. But if I can take, this is also a statistical nature, that if I say no, I am not agree with this, that the crop yield also affects the weather, it is a very, very ridiculous remarks. So what this means, so never think that whenever there is dependency between the variable in the regression set, there is statistical relationship between the variable. It is not necessarily that they are causing each other. Then how we will come to know that, from where we come to know that the variable is causing each other? Come here, and there we have our idea of causation always comes from outside the statistics. Within statistics, we are only find the dependency. The causation relationship becomes, the idea of causation becomes outside of this statistics. For example, I say from the economic theory that says that the crop yield is dependent on the weather, the sunshine, and the other variable. So you should remember what is the key point here. A statistical relationship in itself cannot imply causation. Very, very interesting remarks, that the statistical relationship in itself, there may be very, very strong statistical relationship, dependency between the variable, but you can't say that this is a causality. As I gave the example that if you resist, that you will write the weather on the dependent side, and you will say that now the crop yield is independent. So statistical cannot help us to choose the variable which is the dependent and which is the independent. It is the theory out of statistics. It may come from economics, it may come from finance, its origin may be from other social sciences like psychology, history, and many other things. Now I would like to start from the very simple regression model, that is the simple or bivariate regression model. What is the simple or bivariate? Bivariate means two. Regression analysis is largely concerned with estimating and or predicting the population mean. Keep in mind, we are talking about the regression, and that is the population regression. In every time we are interested to know about the population, and as I said in the previous one or two lectures, that the population cannot be studied. We will be estimating the average value of the population mean on the basis of our sample. So we are interested in estimating the average value of the population mean on the basis of dependent variable and their values are fixed. Example, I would like to give example here. Look at here. I would like say that example is consumption and income. Consumption and income, you know, there is a relationship between the consumption. I would just go 1 minute back to the previous discussion. Here I came another idea. Look at here, C is a function of Y. What we say that when there is change in income, there is changes consumption. It means consumption and income are depending on each other. But who has told us that Y should be on the right side? If I write this one, Y is a function of C, that as consumption changes, income also changes. So these both are regression and these both are statistical relationship that are showing the dependency between the consumption and the income. But on which side now income should be? If I take the second one, this is very interesting. हमें घर बैठे रहना चाहिए, कंजम्पशन बढ़ाते रहें, इनकम हमारी खुद ब खुद जो है वो बढ़ती रहेगी. दिस इज वेरी रिडिकुलस. सो आई एम श्योर नाउ यू हैव गॉट द आइडिया दैट द रिग्रेशन इज नॉट नेसेसरली causation. The idea of the causation should come outside statistics from any of the discipline. So I am now talking about here the regression, that we are interested in measuring the population mean. So this is consumption. I say that I take variable in this sense. This is our y variable in this side, and this is our x variable, and this is our model. So x variable is going this way, y variable on vertical side. I say that x variable, the people, I have some families whose income is, I would like to write it here. I have the families whose income is $80, $80, 80 rupees, 80,000, 80 millions. Need not worry about the scale of this. 80, the other families are 100. I am fixing the x values. The other has 200. I say there are families whose consumption, there are many families whose income level is 80 rupees and their consumption level is, for example, 50, 60, 65, 70 and whatsoever. Similarly, there are families whose income is 100 and their consumption is, I say that 80, 85, 90 and even 95, and I can say that here it is 60. There are other families who has the income level of 200. So what this means, they have 150, 140, 160, 180. Do not confuse yourself that I have deliberately not taken the scale here, because you can see here 50 is equal to here 60, and this way I am avoiding this deliberately. So what this means, if now there are, see, for example, now I am not calculating if here is the mean, here is the mean and here is the mean. So the regression line will go through this. So my purpose was not to just give you the regression line, because I have also showed this regression line before. Now my purpose was to tell you what is the expected mean, what is the expected mean, and what is the conditional mean. What is the difference between, in this sense we write that the expected value of y, that is the average of y, and here we write that it is the expected value of y given xi. So now there are two different concepts. One is the expected value of y. If I come here, I would sum up all the consumption expenditure. If I want to see the average of consumption, this is the consumption side, consumption, and this is the income. Y for income and C for. If I add up all the consumption, we add up this, this and this and divide by total number 1, 2, 3, 4 and so on. For example, if the total, now I am supposing, now just do not concentrate on this, that the summation may be difficult because I am supposing to save the time. So if it is, for example, it is 100 and it is 1000, this is, and the number of families is 20, so the average consumption is 50. This 50 is unconditional mean, not the conditional mean. It is not showing that the families whose income is 80, what is their average consumption and what is the average consumption of the families who have $100 or 100 rupees. So it is giving us the overall picture, and you say the average is a good representation, but it hides many of the information, because it is telling us that all the families, the overall average of the sample is 50, population is 50. So this is called the unconditional, or you can say the expected mean. Here is the conditional mean, and that is called the expected, and we write it expected value of y given x. Now you can see there are three expected conditional mean. One is here, one is there, and one is there. For example, the expected value of y given this xi, the families whose income is 80, for example, their average is, I say 60, I am supposing 60. Here the expected value of y given x2, this is now x2, this is x1, this is x2, and this is x3. So this is x2, and I suppose that it is equal to 80. And here the expected value of y given xi, x3, and I suppose it is equal to 150. So these are this 60, this 80 and 150 are now the conditional mean. Now they are giving us a separate picture about the each group of the family. What I am going to say that the values of the now explanatory variables are fixed. So it is, I think, a time to wind up our discussion, and I would like to give you a smart summary of today's discussion. What was the discussion? We started from the correlation. Correlation is one of the very interesting and easy measure, and this is called first quantitative techniques. So it is very simple. What this means, correlation is the degree of association between the variables. It has some characteristic. I will just explain one or two. The first characteristic was it may be positive as well as it may be negative. If it is positive, if it is negative, then we have found the boundaries of this. It can range between -1 and +1, and it can assume the values of +1 as well as the -1. So when it assumes the value of +1, it means there is 100% correlation between, positive correlation between variable x and y. If it assumes -1, it means that the correlation is negative, but it is also 100% correlation. And if it is something between this, if the more closer it is near to 0, the correlation becomes weaker and weaker. And as it goes away, it goes beyond 0, the correlation becomes stronger and stronger. The next quality or the condition was the correlation was, that is, it is symmetric. Symmetric means that it is independent of the scale and the origin. For example, if we change the different series, it becomes the independent of the scale and the origin. And the other was what is the correlation and the causation. Correlation and causation means the correlation is not necessarily the causation. There may be correlation, but it is not necessary that there should be causation. But on the vice versa, it is interesting that when there is causation, there is definitely 100% correlation. Correlation may be strong or it may be weaker. Then we studied about the regression. That was our last discussion. What was the regression? in the previous sense, the regression means that if there is some unusuality or an abnormality in the population, ultimately it regressed towards the normality. It was the universal law of Galton that tells us that if there are some extremes over time, over generations and generation, it leads towards the you can say the normality. And then we talked about that what is the difference between regression and the causation. Regression is only concerned with the dependence of one variable with the other variable. It is a statistical relationship, but causation, regression doesn't tell us that which variable is affecting the other one. So we have to go for some other discipline to know about the causation between the regression and the causation. The statistical is unable, statistic is unable to tell us that what is in which way the causation running from y to x or x to y. Dependency may run, and dependency may be between x and y or y or x. Then I talked about the conditional mean and the unconditional mean. Unconditional mean is the overall picture of your sample or the population, that it is the predicted and it is the average value or the mean value of your population on the basis of fixed values of the independent variable. And what is the conditional mean? It means now we have segregated the independent variable, we have fixed the values of the independent variable on different stages, and then we found that against each fixed value there is another mean, and that is called the conditional mean. The population regression line goes through the regression mean. So this was all about from me for today on the topics of regression, correlation. We will continue our discussion about regression. So thank you very much. Goodbye and Allah Hafiz.